It's important to understand the relationship between your headset's location in the world and what we as developers do with that data. We've previously discussed the player pawn. The origin of the player pawn can be moved around, but the relationship between the real-world space and space inside of Unreal Engine is complex. It's a subject that we could spend a whole course discussing, but in the interest of simplicity, let's visualize it this way. You can move the player around. You can also rotate your head. The player pawn has its own rotation, and your head holds a rotation of its own. When the pawn rotates, your head will also rotate, but keep its own rotational value. The reason why this gets complicated is due to the relationship between the real-world HMD transform data and the relative position of your head within the container pawn. When we move around the level, our debug box becomes unaligned because the logic we wrote is unaware of the current offset, or where your head is relative to the center of your play space. If your head is 30 centimeters away from the center, we need to add that offset to the draw box. We also could zero out the offset, and this is what is called recentering. By default, the camera in your pawn, or what you see, inherits the real-world offset from the center of the play space. But what if we want the camera to be in the center of our pawn without asking the user to move to the center of the room? We recenter. Or in the case of Unreal Engine, we use the reset orientation and position function. We are going to modify our motion controller pawn darts so that we can recenter with the press of a button. After we can recenter, we are going to go back to our drawbox function and make sure it aligns properly. It's important to understand that this is only for testing. Usually this type of behavior would be scripted within the player controller or a separate blueprint. To get started, we need to bind a new input to a specific button on our Oculus Touch controller. Currently, there's no behavior scripted for Oculus Touch B button, so we will use that. Before we can use that input in our blueprint, we need to assign it in the input section of project settings. Open up the project settings window and have a look at the category section on the left-hand side. Scroll through the list until you see the category Engine. Under that category is Input, and select it. Now you will see all the options for input on the right side of the window. Near the very top of the list is the action mappings. These are specifically meant for Boolean button presses, buttons that are either on or off. Click on the plus button, and if you don't see any options here, you can click on the drop-down to display what action mappings are already here. You will now see a new line labeled New Action Mapping. Let's go ahead and rename that to Reset Origin. In the drop-down next to your new label, you will see a new section for assigning the actual input. The default is set to None. Click it, and now you can search for Oculus Touch RB Press. Be careful to select Oculus Touch RB Press, because that is going to account for an actual press of the key. And as it says, Oculus Touch RB Touch is going to be fired the second you touch the key, not actually pressing it. Now our input is assigned to a new event which we can use in our blueprint. Open up our motion controller pawn darts. Inside of darts, character, VR pawn, motion controller pawn darts. We can now search for our input event. Right-click and search for Reset Origin. If it does not show up for you, double-check your spelling back in the project settings to make sure that it is indeed Reset Origin. Now we have a way to call a function pressing the B on the touch controller. With this new node, we want to call a function named Reset Orientation and Position. Now, when you launch the level, you will notice that each time you press the B button, your perspective slightly shifts. This is the camera returning to the origin point, or the center of the pawn. I'm gonna look this way, and I press B, and now the camera is now centered to me in my play space, which you can see has been changed. If I teleport, or I'll teleport and turn around, maybe I want to look this way, and I'll press B again, and I've been recentered. The pawn has been switched to face my direction now. This is an important function to have for users to center themselves. We as developers have the ability to put a player pawn exactly where we want, but without recentering our HMD, we wouldn't be able to place the user's camera where we want it. We often build logic to drive recentering for the user. It's common practice to recenter a user at the beginning of your application to achieve a baseline of where the user is sitting or standing in their play space. You will notice that if you teleport, the box can become unaligned. This is because, again, of the complex relationship between your real-world play space and the local and world space of your level. Let's see what this looks like in VR. I'm looking forward, so my pawn is facing the table, pretty much. And when I recenter, it's going to always place my camera in the same spot. So if I continue looking this way, I'm still looking in the direction that the pawn is looking, right? So if I want to teleport up here and face the bricks here, I can also do that. Now my pawn has been rotated, and if I recenter, I'm now facing the direction that my pawn is setting, and I'm in the proper location in my play space. But you could see that the play space has been totally unaligned. Let's modify our blueprint to handle this issue. Fortunately, at this point, there is one portion of the transform which we are not going to change, which is the scale. If you were, though, to dynamically change the scale of your player character, then you would want to account for that change, but we will keep it as is for now. We're going to handle the rotation first. To calculate the proper rotation to draw our box, we need to combine the offset from our headset to the play area transform. First, we need to extract the data from Oculus, which relates to the offset. Right-click and search for the function called getBaseRotation and baseOffset, which has two returns, an offset rotation and an offset vector. The first thing we want to do with our rotation is to invert it. We want to remove the offset so that we can use it to subtract. Drag off of the out rotation and search for invert rotator. Now that our rotation is inverted, we are going to combine it with our original rotation from the getPlayerArea transform. To do this, pull off the player area rotation value and search for combine rotators function. This should automatically occupy the A value of the new function. Then we want to connect the output of our invert rotator into the B input. The order here is important as this is a mathematical function. Now you can connect the return value of the combine into the draw debug box rotation. Replug in the extent. When you play the level now, move the character and recenter. You will notice that the orientation of the box is correct, but the location shifts around in a strange way. The reason this is happening is because the location data also needs to be rotated. Back in the graph, we need to do a little bit more math with the offset function. From the out base offset in meters node, drag and search for the rotate vector function. There are many vector math functions with similar names. It's important to choose the one with the exact name rotate vector. This function is taking the world space location of our play space and transforming it into the local space of the player pawn. The rotation input B needs to come from the combine rotators function we recently created. Next, we need to multiply the value from our rotate vector. You may recall that the vector data that we're working with here comes from the out base offset in meters. We need to convert the meters into centimeters. To do this, we need to multiply the vector by a float. Inside of the new multiply node, enter the value 100. Finally, there is one more math function we need to run. Originally, the draw debug box function was using the getActorLocation node, which was reporting back the pawn location. We need to subtract the rotated vector from the player pawn. Drag from the getActorLocation node and search for subtract vector, or vector minus vector. The top input value for this node should be occupied. Now we just need to plug in the output of our multiply rotate vector into the bottom value. Now the output of this subtraction can be plugged into the center input of the draw debug box function. Press play in VR. As you teleport the character around the world, you will notice that the box is no longer shifting around. When you recenter using the Oculus Touch controller, the box will account for it and stay in place. We now know exactly where our user's player space extends in our digital world. Our logic is simply using this data to draw a box, but the same data can be used for other things. We can use it to check if an interactable object is within reach of the user. We can use it to generate level layouts to better conform to the unique player space. We could also use it to create special events when the player gets close to the edge of their play space. Please keep in mind that if a user decides not to enable Guardian, we will not be able to use the return data from the Guardian data, such as location, rotation, and the bounds. Earlier in this module, we used a Boolean value to print whether the guardian was enabled or not. You as a developer could use that output to prompt the user if the guardian was not configured to take action to resolve the issue. In the last module of this course, we'll collect the final assets we will need for the remainder of this learning path.